Welcome to the Walton Pi. Today I'm going over rewriting polynomials and rational functions, which is the 6th video in my AP Precalculus series. So let's just start by talking about polynomials. So far we've either written polynomials in two ways. First, the standard form, where we just write something like x cubed plus x squared minus 14x minus 24. We just write out all the terms. The other way that we've written it has been in factored form, where we write it as x plus 2 times x plus 3 times x minus 4. These two polynomials happen to be the same, but they're just written differently. And then what we're now going to be doing is rational functions. Those are quotients of polynomials, so they're going to be written in very similar ways. We can either write them as the entire polynomial divided by the other entire polynomial, or we can factor both the numerator and denominator of these polynomials. So knowing how these rational functions factor, that's going to give us quite a bit of information. For example, if we look at f of x is x plus 2 times x plus 3 times x minus 4, we immediately see that f of x has a 0 at -2, -3, and +4, but that's not entirely immediately clear from just the standard form. Now, if this polynomial shows up in a rational function, such as x plus 2 times x plus 1 all over this polynomial f of x, x plus 2 times x plus 3 times x minus 4, then that gives us even more information. Here, what we can do is we can look at the numerator. We have x plus 1 that appears in the numerator, but not in the denominator. So that tells us that x equals -1. That's going to be a 0 of the function. And then x plus 2, that appears in both the numerator and denominator. So that tells us that x equals -2 is going to be a whole in the function. And then -2, -3, and +4, those are the zeros of the denominator. That means that the domain of our rational function is all real numbers except these ones. Now we have x plus 3 and x minus 4. Those appear in the denominator but not in the numerator. So that means that x equals -3 and x equals +4. Those are going to be vertical asymptotes of a rational function. A lot of information can be found by using the factored forms of polynomials. So we're going to be wanting to figure out how to do that in the future. Now, our function r of x can be rewritten to be in our standard form, namely where r of x is equal to x squared plus 3x plus 2 divided by x cubed plus x squared minus 14x minus 24. This form is most helpful when we're trying to figure out the long-term end behavior of the function. So for example, here, as x grows very large, both the numerator and denominator grow to be large positive values. However, the denominator is a degree 3 polynomial, while the numerator is a degree 2 polynomial. Whenever the denominator is a higher degree than the numerator, then we know that the function is going to tend to 0 as x grows very large, either in the positive direction or in the negative direction. Now, let's look at this function, okay? As x becomes a very large positive number, both the numerator and denominator are going to be positive. Since the function is tending to 0, that means that the function is approaching 0 from above. It's going to be approaching 0 and will always be positive. Now, as x becomes a large negative number, the numerator is going to be positive, but the denominator is going to be negative. So this is still tending to 0 as x becomes very negative, but instead it's going to tend to 0 from below, since the function as a whole is going to be negative the entire way off towards -infinity. Now, if the numerator is a higher degree than the denominator, then as x grows very large, either in the positive or negative direction, then the function is going to tend either towards positive or negative infinity, again depending on what the numerator and denominator, what their signs are as x grows very large. To determine which, you just have to check those signs of the numerator and denominator, and then that'll tell you all the information you need. Now, if the numerator and denominator are the same degree, things get a little bit trickier. So for example, r of x is 3x cubed minus 4x plus 7 divided by 2x cubed minus 6x squared plus 6x minus 3. As x grows very large, eventually only the x cubed terms matter. Everything else is drowned out by the x cubed because that is the stuff that happens the fastest. So to figure out what r of x tends to, we only need to look at the x cubed terms. So here the numerator is essentially going to just be 3x cubed, and the denominator is essentially just 2x cubed. So as x grows very large, the function is essentially just going to boil down to being 3 over 2. So that means as x grows very large, the function tends towards 3/2 in either direction. So let's tie all of this together and try and match some functions to some graphs. So which of these three graphs is the function y equals x cubed minus 7x plus 6? Pause the video and try and figure this out on your own. Alright, I hope that you were able to try and figure this out. Let's go through this together. So this very last function, this is an even degree polynomial, because we can tell that because the end behavior in both sides is going off to the same thing. Y equals x cubed minus 7x plus 6, that's an even degree polynomial, that's an odd degree polynomial, sorry. So that means that this is not going to be the correct function. Now this first graph, if we plug in x equals -2, we get y equals, into our original function, we get -8 minus 7 times -2 plus 6, which ends up being 12. And so in this red graph, this very first graph, we have x equals -2 as a 0, but -2 is not a 0 of our function, so we can eliminate that graph. And then what we are left with is this one. It's an odd degree polynomial, and the zeros match the zeros of the function. You can test that, plug in -3, +1, and +2. All of those make this function 0, and so this is in fact the graph of the function. Now let's do the same thing with a rational function. Which of these three graphs is the function y equals 2 times x minus 2 all over x squared minus 1? Again, pause the video and try and figure this out on your own, and we'll get back in about 3 seconds. Okay, hopefully you're able to figure that out. Pause it if you didn't. So this first one, we don't have vertical asymptotes at x equals 1 and -1. Those are both places where the denominator is 0 and the numerator is not 0, so we should be having vertical asymptotes. So we can eliminate this graph. This first function, this has vertical asymptotes at the correct places. We have a vertical asymptote at -1 and +1, but so does the last function, so that didn't tell us anything. We also have, for this first function, a 0 in the correct spot at x equals 2, because that's a spot where the numerator is 0, but the denominator is not. But the last function also has a 0 in the correct spot, so that hasn't told us anything. Okay, this first graph, this is positive when x is 0, and the second graph is negative when x is 0. So let's just plug in x equals 0 and see what we get. So we plug in 0 into 2 times x minus 2 all over x squared minus 1. We get 2 times 0 minus 2 all over 0 squared minus 1. That's -4 over -1, which is +4. So we know it's the first graph because that is a function that has the correct asymptotes, it has the correct 0, and it has the correct point when x equals 0. So this first graph is going to be the graph of the function y equals 2 times x minus 2 all over x squared minus 1. Now, going from factored form to the standard form is just really careful polynomial multiplication. Sometimes there's some nice patterns that will help this multiplication, but other times it's just going to be a very tedious multiplication. Now, factoring large polynomials, that's an even more challenging thing, but there are going to be some methods that allow us to do that. So the first step is to figure out what's a potential factor of the polynomial. So if you have a graph of the polynomial, look for the x-intercepts. If the polynomial is 0 at x equals a, then the linear term x minus a is going to be a factor of the polynomial. If you don't have a graph, try factors x minus a, where a divides the constant term of the polynomial. For example, if our polynomial is x squared plus 5x plus 6, some possible a values to try would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Note that in this case, it turns out to factor as x plus 2 times x plus 3, and those were values that we would have found by trying all of these different factors. So now let's look at an example to try and figure out the process of this. We have the polynomial x to the 4th plus x cubed minus 19x squared plus 11x plus 30. We are trying to figure out what is a factor that goes into this. Now, we're looking for what is something that divides 30? 3. 3 divides 30. So let's try and see if x minus 3 divides into this. Okay, how many times does x minus 3 go into that? Well, it goes into the x to the 4th term, x cubed times. So now we're going to multiply out the x cubed times x minus 3, and we get x to the 4th minus 3x cubed, and we're going to be subtracting that from our polynomial. So when we subtract that out, we end up with 4x cubed minus 19x squared plus the 11x plus 30. I'm just not writing that because that's not super pertinent at the moment. But now what we're doing is we're saying, okay, how many times does x minus 3 go into that? How many times does it go into 4x cubed minus 19x squared plus 11x plus 30? Well, it'll go in at least 4x squared times. So we have a plus 4x squared and we multiply that out and we get 4x cubed minus 12x squared. Again, we're going to subtract that through. And so we're left with negative 7x squared plus 11x plus 30. How many times does x minus 3 go into that? Well, it goes in minus 7x times. So we multiply negative 7x by x minus 3. We get negative 7x squared plus 21x. We subtract that off and we're left with negative 10x plus 30. How many times does x minus 3 go into that? Negative 10 times. And when we subtract that multiplication off, we end up with 0. If you end up with 0, that means that it is in fact a factor. So this tells us that x to the fourth plus x cubed minus 19x squared plus 11x plus 30 is x minus 3 times x cubed plus 4x squared minus 7x minus 10. If we end up with something that's not 0 once you've gotten to the constant term, that means that that was not a factor and you're going to have to try again. That's the best I got. It's just a lot of guess and check, and this is just the way that you check. Now, if we're multiplying stuff out, the binomial theorem is one way that helps us out in figuring out some of these different things. So the binomial theorem tells us the coefficients of a plus b to the n. It says that the coefficients correspond to the nth row of Pascal's triangle. Here's Pascal's triangle. We start at the very top where we just have the single one. That is the 0th row. So it is a little tricky. It's not the first row, it's the 0th row. Then the 1, 1, that's the first row. 1, 2, 1 is the second row. 1, 3, 3, 1 is the third row. 1, 4, 6, 4, 1 is the fourth row, and so on. So for example, if we look at a plus b to the fourth, that's 1a to the fourth plus 4a cubed b to the first plus 6a squared b squared plus 4a to the 1b to the 3 plus 1b to the 4. That's how this is going to expand out. We can use this to figure out the standard expression for polynomials like x plus 3 to the fifth. That's not something that we want to have to multiply out by hand, so we hope that we can use the Pascal's triangle and the binomial theorem to figure this out, and we can. We look at the fifth row, because this is x plus 3 to the fifth. So there's our fifth row highlighted, and we're going to expand that out. This is going to be 1 times x to the fifth, plus 5 times x to the 4, 3 to the 1. Then we have 10 x to the 3, 3 to the 2, plus 10 x to the 2, 3 to the 3, plus 5 x to the 1, 3 to the 4, plus 1, 3 to the 5. Note that our powers of x are decreasing by 1 each time, and our powers of 3 are increasing by 1 each time, and that's just how we expand this out along with the coefficients from Pascal's triangle. So that is our full expression. Multiplying everything out gives us x to the fifth plus 15x squared, x to the fourth plus 90x cubed plus 270x squared plus 405x plus 243, and that is our standard form. We can also use this for things like 2x plus 7 to the third. So, because it's the third, we're using the third row of Pascal's triangle. So what we have is we have 1 times 2x cubed plus 3 times 2x all squared times 7 to the 1 plus 3 times 2x all to the 1 times 7 squared plus 1 times 7 cubed. And then when we multiply all of that out, we get 8x cubed plus 84x squared plus 294x plus 343. We can be able to do this no matter what those values are. You just have to be very careful with the parentheses and how you group everything. I hope this video was helpful. If it was, please like and subscribe. Please comment down below any problems that you would like to see me work through in a separate video. And I hope you have a great rest of your day and good luck with all of your math.